702 and Cape Talk.
The Naked Scientist.
Chris, good morning.
Hey, morning, Eusebius.
We start with a really interesting story, lumps and bumps on the Earth's surface. We kind of knew they were there, but the German Space Agency is helping us to see this better.
Yep, we've now got a really fantastic 3D map of the surface of the Earth. All 148 million square kilometres of the land area on Earth mapped from space. Now, obviously, we've had pictures from space for a long time, but what the German Space Agency have done, and they've made freely available, it's in the public domain from this week, is they have published the results of this mission. It started in 2007. Another satellite joined this in 2010. So what they've got is this brace of satellites. One of them is called TerraSAR X. The other one's called Tandem X. And they fly really close together. They're in some cases as little as 200 metres apart. They're beaming down microwaves, which are a form of light, onto the Earth's surface. It reflects off the Earth's surface, comes back up, and because they've got two satellites looking at this beam, they can time how long the beam takes to get back to each independently. And in this way, they've got stereoscopic view of the Earth's surface, so they can map out all of the ridges and folds and the lumps and the bumps. So we now have these amazing pictures of the entire Earth surface. And as I say, it's freely available, and people are saying, well, this could be very useful for a range of reasons. One, you can plan flood risk, you can plan flood mitigation because you can see where the high and the low points are. They're also saying it's going to be really useful for modelling things like climate change, because the next generation of this project is going to use a slightly longer wavelength. It's going to be called Tandem L, for the slightly longer microwave wavelengths they're going to use. And this will mean they can see not just where the tree tops are, they'll be able to see where the tree bottom is. So you can use the two projects to actually work out how tall the tree canopy, how much biomass there is on Earth, because at the moment we've no idea how much plant matter there is. Therefore, we don't know how much carbon is locked up in that aspect of the biosphere. This will help to tell us. So if you want to go and have a look at it, just look up the German Space Agency website. It's just awe-inspiring.
Beautiful. Stunning. Bandile, good morning to you. Welcome to the show.
Good morning to the Naked Scientist and to you, Eusebius. My question is on how do scientists, and especially in the history of science, how have they been able to calculate the mass and the velocity of planets in order for them to, map out the orbits? So how would someone like Newton or Galileo know that his laws were true without what tools did he use to calculate mass and velocity of entire planets? Thank you.
Hi, Bandile. I think it was actually Archimedes who said, give me a lever long enough and a place far enough away to stand and I could lift the Earth. And he wasn't speaking in a small way, because the Earth is very massive. It's about 6 followed by 24 zeros kilograms, so 6 followed by 21 zeros tons. It's pretty big. How do we know that? Well, there's a range of ways. One of them is that you know what works on the small scale. So Newton was able to make his calculations on the small scale and then scale them up to the big scale and found that they still pretty much worked. We basically know what planets like the Earth are made of, and therefore we can calculate, if we know how big they are, we can calculate what their density must be. So we can do all these sorts of calculations by inference, and then we can prove them by actually doing further experiments. So basically, people like Newton, very bright guy, worked out these things on paper on the small scale, extrapolated them to the big scale, found they still worked, and then said, there you go. But the bottom line is, we know what something like the Earth is made of. We know what its density is. We know by looking at things like the moon how it influences the moon and the moon's behaviour, so we can work out what our planet is made of and how dense it is. Therefore, we know how massive it is. We can also look at how it influences other things around it elsewhere. And as a result of that, we can work out whether or not we've got the maths right, which it would appear we have.
Jane, good morning. Welcome to the show.
Good morning. Hi, Chris. I'm not sure if this is normal for most people, but I have found when I see an accident happening, or I seem to have been involved in an accident, the whole world seems to go into slow motion. Does that happen?
Lovely question.
Hello, Jane. I hope you don't have too many accidents, but this is a real phenomenon, and psychologists have been studying this, and they wanted to know whether there really is a distortion of a person's perception of time, or whether actually something else means that, in fact, time doesn't slow down, but we think it has. Now, one theory that psychologists have is that when we go through life, we're storing a sequence of mental images and memories about the things that are happening to us. Now, when we end up in an exciting or a dangerous situation, you engage a part of the brain called your amygdala, which is you have one on each side. It's the size of a small coin in the brain. And this network of nerve cells is your fear center. And it profoundly affects the way we behave. It's also very profoundly interconnected with the memory circuits in the brain. When we go into a dangerous or fearful situation, because there's an opportunity to learn from that situation and to make sure we don't end up with history repeating itself, the amygdala increases the density of memory storage. In other words, it encourages you to enrich or profoundly increase how much attention you pay to the things that are happening, and therefore how many memories you lay down. When you therefore look back over the situation, what you see is a very thin memory record of what had led up to the event, but then a very dense, rich series of memories corresponding to the event. And so your brain, because it roughly knows how many memories it's storing over a period of time, we speculate that actually because there's a much richer record corresponding to that time when the fearful thing or the dangerous thing or the accident happened, time must have slowed down because we see so many different facets and so many memories laid down corresponding to that thing. So time didn't really slow down, but your ability to analyse what happened is richer because you have a richer information store. So your perception of what happened during the time has changed. And psychologists have done other studies where they've actually got people doing things and they've engineered into the study that if time had changed for those people, their perception of time had changed in real time, they would have experienced the thing differently, and people don't. So it looks like it's our recall of the event after the fact and the fact that we have a richer memory record that makes us think that time slowed down. It didn't really slow down. We didn't process differently at the time. We just stored a richer memory of it, which made us think that time must have gone slower.
Robert, welcome to the show. What is your question?
Quite simple. Close to home, sodium chloride, table salt. Is it bad for our health, or should we avoid it?
Hi, Robert. Well, this has been a bone of contention for a long time. There have been a lot of studies across the whole world looking at many different cultures, many different genetic makeups and geographies, and the trend would appear to be that the more salt that you eat in your lifetime, the higher your blood pressure ends up being. Now, we don't know why this is. What we do know is that it seems to increase the volume of blood in circulation, which in turn increases the blood pressure. But whether the salt causes that or whether the salt does something else that then causes that, actually, we don't know. I interviewed a scientist earlier this year called Dominik Müller, who's working in Germany, and what he has been doing is experiments on mice where he shows that if you feed mice a high salt diet, it changes the makeup of bacteria in their intestines because the bacteria eat what we eat. So if we eat something different, the bacteria eat something different and they change. He finds that when you change those bacteria, you can give mice high blood pressure, just like you can humans. But if you give the mice probiotics, and specifically things like lactobacilli, which are in a lot of these yogurt drinks, you can mitigate the blood pressure elevating effect of a high salt diet. So this puts the cat among the pigeons a bit, because is it the salt directly affecting the body and affecting the amount of blood and therefore blood volume that causes the high blood pressure? Or is there something else going on? Is the salt affecting your microbiome, the bugs that live in you, and are they then doing something? Perhaps they're changing the way your immune system works. We don't know. And that in turn translates into higher blood pressure. But what we do know is that higher salt intake does appear to translate into higher blood pressure, and that in turn translates into a higher risk of heart disease and stroke later in life. So therefore, minimising the amount of salt, but not to the extent where you're salt depleted, is probably a good idea.
Brian, good morning. Welcome to the show.
I just wanted to ask the naked scientists, they have been studying, life science and all of those things about the primates and stuff. So we've been researching and trying to find one of the latest findings of some primates sort of like transitioning into humans, and there's been really, really hard, not even one video. So I just want to ask, maybe he has some insight as to, is it still happening? If not, why is it not happening, the transition from primates to humans and stuff like that? And if he may, why is it that when you give a dog a scorpion or a spider, it gets gets very aggressive. Thank you so much.
Okay, I think it was squeezing in several questions there. You can answer any one that you managed to catch there, Chris.
Well, let's look at the human evolution one, because, of course, this is where South Africa leads the way in the world, because South Africa has probably the richest record of where we came from in terms of fossils and remains of our ancient relatives compared with any other country. So let's talk about what's going on. Well, what we know about human origins is that our earliest ancestors that we share with the primates that were being referred to in the question, it's probably about 6 million years ago or so. So in other words, if we went back in evolutionary time about 6 million years, we would find an animal which, if we followed that animal, it would give rise to descendants that included modern primates like chimpanzees and bonobos, and then another strand from that animal's descendants would ultimately lead to anatomically modern humans, us here in the modern era. The mistake that many people make is they assume that we should suddenly see monkeys turn into people. Evolution happens over millions and millions of years, and it's a series of very small changes in response to pressure from the environment in which you live. So if you live in a certain place and climate change happens or food comes and goes and that kind of thing, you slowly select for groups of individuals that are very good at existing in that environment. And those individuals that are the most successful will have the most offspring, so they will pass those genes that make them look like that, behave like that, etc., into their offspring. This does not happen quickly. It happens very slowly, and it's a very gentle process of adaptation. So the animals that you see around you today are the product of millions of years of nature moulding them and their ancestors to live in the environment and exist in the environment in which they live. So we do have ancestors which we share with chimpanzees and monkeys. We even have ancestors that we share with jellyfish, but you have to go back billions of years to find those. But we're all interrelated, and we know that because of the genetic code. But this process does not mean that we would expect to see a monkey turn into a human or vice versa tomorrow.
702 and Cape Talk.
The Naked Scientist.
George, what's your science question?
The question I want to ask relates to weight or mass, for instance, of the clouds, right? Sometimes it rains to a point where, it even floods, causes flooding and all that. And obviously that's a huge amount of water. So the question is, how come someone, let's say a human being or an object like a human being cannot hang up there because of the force of gravity, and yet clouds themselves with so much water in them, and I know it's in an uncondensed form, are able to float and that's my question. I don't know if it makes any sense.
Hello, George. Basically what you're saying is how much does a cloud weigh? And why is a cloud that weighs, I'll tell you, the equivalent of hundreds of elephants, to take an African analogy, up in the sky? Well, the reason is clouds are big and the particles of water that are in them are small. And when the water first goes up in the atmosphere, it's in the form of water vapour, which are individual molecules or small groups of molecules joined together. And as it rises higher, air expands and cools, and it can't carry this water vapour anymore, so the water vapour condenses into small droplets. Those are raindrops. And because the temperature is so low, they actually freeze. And so most of the rain that lands on the Earth's surface is actually in the form of ice crystals when it's way up in the atmosphere. But the thing is, what's keeping the clouds up there is that the warm air from the Earth's surface is rising all the time and creating an upcurrent. So this is pushing stuff up. So there's always a sort of tension going on between the water, which is being accelerated down by gravity, it wants to fall out of the cloud, and the updraft pushing it upwards. And as these ice crystals get larger and more numerous as the cloud grows, and more water is added because more damp air rises from the Earth's surface, then eventually you get to a threshold point where the acceleration due to gravity on those massive water in the cloud is greater than the updraft, and the water begins to fall. Now, much will evaporate, actually, before it hits the ground. Something like a half to 3/4 of the water that falls out of a rain cloud may re-evaporate on its way down to the earth and never reach the ground. It goes back up and makes the cloud again. But the water that does make it down to the ground then, as you say, waters the ground and in some catastrophic cases makes a flood. But that's why the clouds, they are enormous. They weigh, there are millions of tons of water up there in clouds above the Earth's surface, but they're in the form of tiny particles, which are ice crystals being held aloft by updrafts. And it's only when the cloud has to become even more massive, or you try and make the air rise higher, and you condense more water out of the air and make those particles bigger than the updraft is capable of supporting, that's when the rain can come down.
Let's take one from social media. Here's a question from Dane for you, Chris. I've got deja vu around this one, but I don't know the answer. I think you've answered it before. Why do cockroaches almost always end up on their back when they die?
Well, I think you're more likely to find them that way. One reason for this is that the back of a cockroach is a nice curved shell, and it's a fairly stable surface. So if you flip a cockroach over, then it's probably going to stay like that because it hasn't got legs to flip itself back the other way once it's on its back, so it's much harder for it to turn over. So when a cockroach ends up in its death throes, if its legs happen to work on one side but not the other, it might end up falling onto its back, and because it's dying, it can't right itself or doesn't bother to right itself, and the relative stability of it being on its back means it's more likely to stay that way. That's one reason. Another possibility is that as the animal dies and goes into some sort of rigor mortis, its muscles might contract on one side more than the other temporarily and actually ping it over. And then, of course, it's dead, and it won't move from that point. So you're going from a position of relative instability, legs that move around and push a body up and down, to one of stability, which is harder to reverse, a flat shell with it on its back. So I think you're more likely to find them on their back when they've died, just because of the fact that it's a more energetically stable situation to be in, and it's less likely they're going to get flipped back over again.
Eve, you've been holding on. Thank you for your patience. What do you want to ask?
I'm interested in the hurricanes. We've seen recently the devastation that's now, and especially this week, caused up in America and those islands. But we also know that these hurricanes originate in Africa. So I want to know, why is it that Africa never sees those hurricanes and it only moves up in one direction? And are we likely to ever see that happening to us, taking climate change into consideration?
Thank you, Eve.
Hello, Eve. Well, actually, hurricanes form over water. They're powered by warm water. And what I was talking about earlier with rising warm air, that's critical to a hurricane. So what happens usually, and the reason America is often a victim, is because the Gulf of Mexico, down where Florida is, gets heated by the sun at the equator over the summer. And as the water temperature goes up and up and up, eventually you get to a point where the water is nice and warm, and the warm water is warming the air above the sea. Warm air rises because it's less dense. So the rising, less dense air, also carrying some water with it, goes upwards, and something has to come in to replace it. Of course, that's cold air, which is coming in from further afield across the planet's surface. The planet's spinning, so the air that gets pulled in to replace the hot, damp, rising air over the Gulf of Mexico is coming from the surface of the Earth, and it's itself spinning. And as it moves in towards this one small place where the air is all evaporated up in where the air has all risen from, you're taking air that was spinning in a giant circle around the Earth, and you're making it move in a much smaller circle in just one place over the Gulf of Mexico. And because of something called conservation of angular momentum, which is that once something is spinning, unless a force acts on it to stop it spinning, it's got to carry on spinning. But because the air is originally going in a very big circle relatively slowly, when you then make it go in a very small circle, because it's still got all this momentum, it accelerates. So the air in fact spins much faster when it's over the Gulf of Mexico, and this fast moving air is what creates the high winds that correspond to a hurricane. And the hurricane then migrates usually north up the coast of South America, up the coast of North America away from the equator, and does all that devastating damage. But the minute it goes over land, because it's that rising tide of warm air and damp air coming off the sea surface, because that's cut off once it's over land, the hurricane will stall and go away. Now, that shouldn't happen in Africa because the geography is quite different. And obviously it's a massive land area, and it's much harder because you haven't got all that water to feed the hurricane. But you can still have very violent storms, as anyone who lives in Joburg and likes thunderstorms will know only too well.
Clyde, good morning.
The question is twofold. First of all, how does one determine how high above sea level you are at different places on the Earth? And secondly, what is actually happening in the air pressure going from sea level to high up on the mountain, for argument's sake?
Thanks, Clyde.
Okay. Well, we know that the Earth is a ball, and the sea clings to that surface owing to acceleration due to gravity, which is pulling the water onto the Earth's surface. The land would be covered in water if we were not above sea level for the most part, but there are some inland areas where there are depressions which can be below sea level, but because the land's in the way, the sea hasn't got there. There are some areas of the sea surface, though, which are higher than they should be. And a really good example of this is if you go down to Antarctica, because there's an enormous amount of ice sitting on the land in Antarctica, that ice has mass. And that mass is gravitationally active, so it actually has the effect of pulling down into the South Pole a big bulge of water, which it holds around Antarctica. So that actually keeps the sea level artificially a bit lower around the rest of the planet than it otherwise should be. Now, the other question that was asked was about air pressure. When you're wandering around on the Earth's surface, the pressure on you, because of the column of air above your head going out into space, is about 10 tons on every square metre. So it's like having an elephant standing on your shoulders. It's very, very large. And we don't feel that because we're used to it and we've got air pressure pushing in on us all the time, so we've adapted to accommodate for that. But as you go up in the air, the amount of air above you is dropping. And if there's less air above you, there's less mass of air above you, and therefore there must be less pressure of air above you. And this is why the air pressure falls as you go up in altitude. And as you go up in altitude, because the air pressure falls, the air expands, and because the air expands, the air gets thinner, and because the air gets thinner, there's less oxygen molecules per cubic metre at the top of, say, Mount Everest than there is at sea level, and that's why you have to breathe a lot harder or take supplementary oxygen with you.
Dennis, squeeze in your one as the final one.
I'm troubled by paradox. They say that the light from the furthest star takes 15 billion years to get to Earth. Does that mean that the universe is actually double the size? Because otherwise, how did the light travel in 15 billion years and the universe continues to expand?
Yeah, hi Dennis. This is a tricky one to get your head around, but if we imagine that the universe, as Stephen Hawking suggested, began from a very tiny point source. This is his work with Roger Penrose from the University of Oxford at the beginning of his career. So the Big Bang is a point source which then begins to inflate the universe, and the universe grows at various rates and becomes this enormous bubble that's blowing up. Then if we look at distant objects in the universe, we see that the light coming to us from them is stretched out, and it's stretched out because the universe is expanding, and we can work out on the basis of how fast the universe is expanding how far back in time these objects must be, etc. And that tells us the universe is in the region of 13.8 billion years old. So in other words, the light that has been travelling towards us has been travelling towards us at the speed of light for 13.8 billion years. And we can still see it. So yes, the universe is expanding as a bubble. The light has travelled through space corresponding to 13.8 billion years of space travel at the speed of light to get to you. So that's the size of the universe between you and the object that emitted that light.
Thanks, Chris. We'll do it again next week. Have a beautiful weekend.
Thanks, Eusebius. Thanks, everyone. See you soon. Bye-bye.